part 2 of our work. This is part 2 of our work, and we are looking at pressure in liquid. Okay, so in part 1, we took a look at general pressure in solid. Is that okay? So without wasting time, let's begin. So this one we call part 2 of pressure part 2. Okay, part 1 we studied pressure, we defined pressure, we gave the unit of pressure, that is Pascal, and 1 Pascal is equals to 1 Newton per meter square, which is force over area. We did that. So we say pressure was force over area, pressure was force over area. Okay, we did this yesterday in part 1 of our video. We say pressure is force over area, especially pressure in solids. We say pressure is force over area. Today we're going to look at pressure in liquid. So first of all, quickly, I want to link. If you have a liquid container, we want to link pressure in solid to pressure in liquid. You have a liquid container, you have water. You have water inside. Let's say these particles are particles of water. Okay, you have water inside the liquid. You have water particles inside the liquid. Now you see the water exert pressure on the container, the bottom of the container. The water at the top, or all the volume of the water in the container, exert pressure at the bottom of the container. So we say this force is, in the case of liquid, we can call it weight. So okay, we can say pressure equals to weight over area. Pressure equals to weight over area. And then we know that the weight is defined as mass times gravity. So we can simply say pressure now in this regard is equals to mass times the gravity. Mass times gravity, because it's weight, right? Mass times gravity over area. Now this mass of water can be replaced from the density formula. You know the density formula? We say mass is what? If you look at the density formula, we say density is mass over volume, right? We say density, which is given by this symbol, density is mass over volume. Density is mass over volume. Okay. I know you'll be wondering where are we going with this. Density is mass over. So this mass I want to replace it with density and volume. So in place of instead of writing mass, mass is same as the density multiplied by volume. Density multiplied by volume. Mass is density multiplied by volume. So I can simply write this formula to be density of a liquid, because we are not talking about liquid. So I will talk about the density of a liquid times the volume of the liquid times the G is already there, this G, so I put the G here, over the area. Now this volume, that's another step. So this volume, I want to remember volume simply area multiplied by height of the liquid, the depth of the liquid. We call it height, the depth of the liquid. So this is the height of the liquid. So we simply replace the volume V with area and height. We simply replace it with area and height. So we say the volume, remember the volume is equals to area of a liquid multiplied by the height of the liquid. So when you do that, you not replace this V with A, right? So the new formula of pressure, because we are going to pressure of liquid. I just want to introduce this. You will not find this in most of the book. Okay, I just want to show you this before we go to our tutorial. So we write pressure equals to the density, which is rho. The density, instead of writing the volume, I'm going to replace volume with area and height. So area times area, density times area times the height, volume. This AH replaces the volume. And then after AH, after the volume, we have the gravity. So I put the gravity here. Over what? Over this area. So I always substituted for V. I always substitute AH in place of V. I substituted AH in place of V just the same way I substituted the mass with the density and the volume. We substituted the mass with density and volume. Is that okay? And we substituted the weight. We substituted the weight with mass and gravity. Okay, it's just about substitution from one step to another. Now you see you have A here, you have A at the bottom, you have A at the top. So we can cancel them out. The area on top cancels the area at the bottom. Okay, so now you have what? Real GH. You now have your density formula for liquid. This is how we use the density of solid to derive the density of liquid. So the density of liquid is real GH. That real is density. The pressure, not density of a liquid. The pressure of a liquid is the density multiplied by the gravity, multiplied by the height, multiplied by the height. So this formula, this is how we obtain this formula. Is that okay? This is how we obtain this formula. Okay, this popular formula for calculating the pressure of liquid. This popular formula for calculating the pressure of liquid. This is how we obtain it. We derived it from the ordinary pressure of solid formula. We derived it from the pressure of solid formula. So from here, you see, we walked all the way to this place, and we got that as the formula for calculating the pressure of a liquid. Is that okay? So pressure of a liquid is because of this. Now you've derived the pressure in a liquid is inherently dependent on three big factors. Okay, three big factors. One is the density of the liquid. The pressure in a liquid depends on one, the density. This symbol that looks like E is not E. It's called the density. It's rho. It's a Greek word. It means rho, and it means density. It's rho. It means density. It's a Greek word. Okay, this symbol, rho GH. When we say rho GH, meaning density times gravity times height. Okay, so if they ask you what are the factors, what are the factors affecting the pressure in a liquid? One of the factors affecting the pressure in a liquid is the density of the liquid. The density of the liquid. So if the liquid has a high density, it therefore means the pressure will be great, will be high. The pressure at the bottom of the liquid or at the bottom of the container, the pressure at the bottom of the container will be high. The pressure here at the bottom, the pressure exerted at the bottom of the container will be high if the density of the liquid is high. Like if it's water, water has a very high density. Water has a density of 1,000 kilogram per meter cube. 1,000. So it's a very high density. Water has a very high density. 1,000 kilogram per meter cube. Per meter square. Sorry. Yeah, per meter cube. It's mass over volume. Okay. So this is the density of water. It has a very high density. So one of the factors that affect the pressure, of a liquid or pressure in a liquid is the density of the substance of the liquid itself. If the liquid is oil, then it is the density of the oil that determines how much pressure will be at the bottom of the container. If the liquid is water has a very high density. It means the pressure at the bottom will be high because density is one of the factors affecting the pressure. Density is one of the factors from what we just derived from the formula. So you can use the formula to actually answer this question. If they ask you to give the factor affecting the pressure in a liquid. One is the density of the liquid. It affects the pressure. The greater the density, the more the pressure at the bottom of the container. The more the pressure at the bottom of the container. Another is the gravity. Acceleration due to gravity. So the acceleration due to gravity affects the pressure at the bottom of any lake or container. Then the third one is the depth. We call it depth, height, depth. This word, the depth of the liquid in the container. So if the height is very big, then the pressure at the bottom will be very big as well. If the container is very tall. If it's a flat container with a small height, the pressure here will be small. There will be no much pressure. For example, if you take a container like this and fill it with water, the pressure at the bottom is not so high compared to the pressure at the bottom of this one because of height. Because the density, same, gravity probably same thing. So the density of water is the same thing, whether it's a small container or big container. The only determining one now will be the height, which we call the depth. The depth. The depth is small here compared to here. This one has a small h. This one has a small h. This one has a smaller h. So the height here is small compared to the height here. So the pressure at the bottom here will be bigger than the pressure at the bottom of this one. It will be bigger than the pressure exerted by the liquid at the bottom of this container. So the depth is a big factor that affects so is that okay? That affects the pressure at the bottom of any container, of any liquid in a container. You can also say the weight. The weight is a big factor also. Because pressure is dependent on weight, right? Pressure is dependent on weight. Weight is mass times gravity. When you say weight, you're talking about the gravity as well. You're talking about the mass. Okay? So these are some of the factors that affect the density. I've already mentioned this one. See, the density of the liquid. The weight has something to do with the gravitational force. You can say the weight or the gravity. You can use the word weight or you use the gravity. The bigger the weight, the more the pressure that is exerted at the bottom of the container. The bigger the weight of the liquid, the more the pressure that is exerted at the bottom of the liquid. Okay? The bigger the density of the substance, because different substances have different density. So the bigger the density of that particular liquid, the bigger the density of the liquid, the more the pressure is exerted at the bottom of the container. Okay, so with this, I've given you some of the tips. Now we go to our tutorial. Before we start, we go to our tutorial. Before we go back to pressure in a column of water. Okay. I think we do this one. This one is quickly just itemizing or showing what we've said. If you take a look at this container we have tap. Okay, we have tap at the top, almost at the top, at the medium, and close to the bottom. Okay, now the pressure at the top of the liquid is low. Of course, because only the liquid at the top is exactly pressure somewhere here. But all of the liquid is exactly pressure at the bottom. All of the liquid is exactly pressure at the bottom because of greater height. Because of what? Pressure increases with the depth of the container or of the liquid. Is that okay? Increases with depth. Pressure increases with the depth. The taller the container or the material is, the more the pressure is exerted at the bottom. The more the pressure is exerted by the liquid at the bottom of that container. So for this one, we have a higher pressure than the one on top. We don't say, because this one is at the bottom, so I just say this one low pressure, the one on top high pressure. No, it doesn't work that way. The one at the bottom, the greater pressure is exerted at the bottom of this container than at the top of the container. Okay, so this is a weakest. This water will be coming out from here. Small, little, not with speed. Water will be coming out from here, not with speed. Here will be like normal, will be a normal case. Water will be coming out from here, normal. That's why you see this one is not taking farther away from the container. It's just coming down straight away. Just coming down. This one, the pressure with which the water is coming out, force over area, which is pressure. The pressure with which the water is coming out is relatively at the average. That's why you see it's taking a little bit farther away because of the pressure, a little bit farther away from the container. Here, the pressure is greatest, is highest here. The pressure is highest here. Here the pressure is highest here, so you can see greatest jet. The force per unit area is farther away, you see, because of greater pressure. See, this one is thrown away. The water is taken farther away from the container because the pressure is very high compared to here. Here the pressure is very little, it's very low. So you see the water is like it's drippy. It's not going farther away from the container. So here you can come and put a basin or a beaker here, all the way this way. You can measure the distance to this place, the distance with which this pressure push the water away from itself because of higher pressure. Is that okay? So at the lower part of the container, the pressure is greatest compared to other scenarios. Now let's take a look at, before we go to calculation, before we start doing the calculation of the pressures in a liquid using rho GH, density times gravity times height. Let's quickly take a look at our tutorial. Is that okay? Thank you. Okay, so let's listen to our tutorial.
This video is about pressure in liquids. There are 3 key properties of pressure in liquids. Pressure on an object suspended in a liquid is exerted evenly across the whole surface in all directions. As an object sinks deeper into a liquid, the pressure it experiences increases. This can be observed by punching holes in the side of a full water bottle. The water in the lowest hole flows with the strongest force because of the higher pressure caused by the weight of the water above it. The deeper an object, the more water above it, and the higher the pressure it experiences. The denser a liquid, then the higher the pressure it exerts on an object suspended within it. Honey is denser than liquid soap, water, olive oil, and alcohol. So the pressure it would apply to an object is the highest. It would be much harder for you to swim in a pool of honey than a pool of water because the particles of honey apply higher pressure on your surface than the water particles. The pressure acting upon an object suspended in a liquid depends upon its depth and density. Hence, it can be calculated using the equation pressure in pascals is equal to liquid density in kilograms per meters cubed times gravitational field strength in newtons per kilograms times depth, h, in meters. Don't get confused between P for pressure and the Greek letter rho for density. This worked example is about the pressure on a scuba diver when underwater. A scuba diver of mass 53 kilograms is at a depth of 42 meters below the surface of the water in the Red Sea. The density of the water is 1,029 kilograms per meters cubed, and the gravitational field strength is taken to be 9.8 newtons per kilogram. Part 1 asks you to describe whether the pressure on the diver would be higher or lower if he was diving at the same depth in a freshwater lake for 2 marks. The key concept to recognize here is that the density of the salt water in the Red Sea is higher than the density of the fresh water in the lake for 1 mark. So the pressure exerted on the diver in the fresh water at the same depth will be less for the 2nd mark. Part 2 is to calculate the pressure exerted on the diver in the Red Sea for 2 marks. Step 1 is to substitute the values into the equation for pressure in a liquid. Pressure is equal to density times gravitational field strength times depth. Density is 1,029 kilograms per meters cubed, times gravitational field strength, which is 9.8 newtons per kilograms, and depth, which is 42 meters, for 1 mark. Don't be distracted by the mass of the diver. You don't need this to complete your calculation. Now calculate the pressure. Pressure is equal to 423536.4, which is equal to 0.4 times 10 to the power of 6 pascals, which is equal to 0.4 megapascals for 1 mark. This is a big number. We can use standard form or the prefix mega to make it look nicer and easier to understand. 1 times 10 to the power of 3 gives the prefix kilo, like kilometers, and 1 times 10 to the power of 6 is equal to mega, like megabyte. In summary, pressure on an object suspended in a liquid is exerted evenly across the entire surface, and it increases as the object descends deeper into the liquid because of the increased weight of the water above, and it increases when surrounded by a denser liquid because there are more particles in contact with the object's surface. Pressure is calculated using the equation pressure in pascals is equal to density in kilograms per meters cubed times gravitational field strength in newtons per kilograms times the height or the depth in meters. Salt water is denser than fresh water, so the pressure applied on an object suspended in salt water is greater than in fresh water at the same depth. Don't forget to check out all our other fantastic revision resources.
Okay, so that was the tutorial. Tutorial really talked briefly about pressure in liquid. Is that okay? Just briefly about pressure in liquid, and also letting us know that pressure in liquid is acting at all directions. Okay, the water is exerting pressure on this wall, this surface, everywhere. The pressure is at everywhere. Okay, it's uniform. It's uniform and everywhere. Now the formula for calculating the pressure in a liquid, which we have already derived, we derived it ourselves, is the density of the liquid, the density in kilogram per meter cube, times the gravity in Newton per kilogram, times the height in meter, or the depth. Okay, so this is the formula for calculating the pressure in liquid. Okay, so 1 Pascal, like we already established in part 1 of the video, we say 1 Pascal is equal to 1 Newton per meter square. 1 Pascal is equal to 1 Newton per meter square. And we know the formula for the density, the unit of the density of a liquid is kilogram per meter cube, right? Okay, the unit for the density, as we've done in chapter 1, chapter 2 of this material, the unit of density is kilogram per meter cube. Kilogram per meter cube. Okay, the unit of density is kilogram per meter cube, as we stated, and the gravity, G is the gravitational field strength on Earth. Okay, measured in Newton per kilogram. G, sometimes we can say meter per second square. It's also possible to say meter per second square, but the most notable unit for G, this is acceleration. Meter per second square is acceleration, but the most notable unit is Newton per kilogram, because you can get your G by making your weight formula the G the subject of a formula. Okay, right? This is your gravity. Weight is your weight is mass times gravity, right? Your weight is mass times gravity. So if you make G the subject of formula, you say G is weight over this. Weight is in Newton, and the mass is in kilogram. This is how the unit is Newton per kilogram. Okay, everything can be derived in physics. So this is the unit of your G, Newton per kilogram. Is that okay? Now your delta H is the change in your height, change in the height of the liquid, measured in meter. Is that okay? So we have this pressure in liquid with density. Pressure in liquid with density, with a density is applied at the depth. Okay, at a depth. Let's take a look at this. We have a substance put in a liquid. We have a distance, the depth to the substance, right? Maybe like a ball or something. And then we have pressure of the water acting, pressure of the liquid will be acting on this material from all directions. So pressure in a liquid will act on any material in the liquid from all directions. Is that okay? So this point you need to know, because in multiple choice exam, they will ask this question. Pressure will act in all directions. Okay? Pressure acts in all directions. In a liquid, any material in a liquid, pressure will act in all directions. Is that okay? Okay. Pressure acts in all directions. Sorry, okay, for trying to plug my computer. Okay, so we say pressure in a liquid acts in all directions. If you have a metal, you put it in the water, the pressure of the liquid will act on the metal from all directions. So pressure will act on it from all directions. Okay? Now let's take a look at a question. It says calculate the depth of water. They want us to calculate the depth. Okay? Now they are not asking us to calculate the pressure. Calculate the depth of water in a swimming pool. The depth means the height of water in a swimming pool. Here the pressure. Here they've given us the pressure. 20 kilopascal is exerted. The density of the water is 1000. This is a constant value. And the gravitational field strength is 9.8. So we go to write our formula. Pressure formula in a liquid. You must write pressure in a liquid formula. In a liquid, when they're talking about liquid, don't say F equals to P equals to F over A. No, that's for solid. That's the pressure formula for solid. So you must know these two formulas. Okay? So pressure in a liquid is density in density times gravitational field strength. Density times gravitational field strength times the height. Remember now they are asking us to calculate the height, the depth. So you're going to make h the subject. To make h the subject, you divide both sides by density and gravity. So we're going to divide both sides by density and gravity, okay, in order to find the height. So we divide here by density. We divide here by density and gravity. We do likewise here. We do the same here. Divide by density and gravity. So this density and gravity here, we cancel the ones here. So our height formula is now obtained. So our height is equal to the pressure divided by the pressure in the liquid divided by the density and the gravity. Divided by density multiplied by gravity. Okay? So this is the formula we're going to use. Now we're going to write out our parameters. These are called parameters. When I say parameters, the height is a parameter, the pressure is a parameter, the density is a parameter, the gravity is a parameter in physics. Every physical quantity you mention is a parameter. Remember the pressure is 20 kilopascal. So 20 kilopascal is 20,000 pascal. Okay, so when we write 20,000, don't be wondering, we just converted kilo to the ordinary number. Remove the prefix, the kilo. Kilo means 1,000. Okay, so 20 kilo means 20,000 pascal. So this is the pressure you're going to use. Okay, you're not going to use the kilo in the formula. You're going to put in the pascal format. Okay, now we have the density of the liquid, of the water, which is 1,000 kilogram per meter cube. 1,000 kilogram per meter cube. This is the density. So we write the values out, and then we will substitute the values into the formula. So it's very easy. Physics is very easy. Bring out your parameter, know the formula to use, and then key in the formula to it. Our gravity, G, is equals to 9.8. Remember this from 2025, Cambridge IGCSE will be using 9.8 for gravity. Okay, so we better get used to using 9.8. It used to be 10 approximately, okay, but now they will be using 9.8. And so read your exam paper at the front page. So if they are keeping 9.8 for you, they will state it in the first page of the paper where the instructions are. If they're going to change it to 10, if it still remain 10, they will also state it there, what to use. So throughout the paper, you stick to that value, whatever is stated on the top of the paper. So here we're going to we substitute it to this formula. The pressure is 20,000 pascal. Okay, remember we converted 20 kilopascal to 20,000 pascal. So we put the values here, 20,000 over our density, which is 1,000. 1,000 times this, we can just have 9,800, right? If we multiply, because we are supposed to multiply these two values. Okay, we write 9.8 times 1,000, 9.8 times 1,000. Okay. Ordinarily, these 3 zeros, we cancel these 3 zeros. So what we have left is 20 divided by this. So when you divide, what do you get? Okay. You divide this one, you get 2.0408. Okay, so we get height h equals to 2. Because it's like 20 divided by 9.8, 2.0408, something like that. So this one we can approximate to the nearest whole number. When we do that, we have h to be 2 meters. So the depth of the substance is 2 meters only. Is that okay? Okay, so the depth is 2 meters only. Is that okay? So that's 2.0. 2004. Say divide. What do you do? Don't know, you multiply the denominator first. Now, so I think that's what now we want to talk a little bit. We've talked about the pressure in the liquid already. Pressure in liquid increases with the depth. We mentioned this, okay? Just a recap of what we've talked about. It decreases with the depth and also the density of the liquid. And we say the pressure at one depth acts equally in all directions. Pressure at one depth acts equally in all directions, okay? And then we say the pressure here is greater. So there's greater force pushing this water out from here than from here. There's greater force pushing water out from here at the bottom than from the top. Okay, in case you see this in multiple choice. The pressure here is bigger than the pressure. Here is low pressure, here is high pressure. Okay, so then we say a liquid finds its own level. Okay. We also say pressure depends on the density of the liquid. The bigger the density of the liquid, the bigger the pressure that is exerted. Is that okay? Okay, so here we've talked about all of this. We've derived the formula. We've derived pressure is depth times density times gravity. We've derived this formula, okay? And then we say the pressure is smaller for solid. Pressure is smaller in the smaller area when the area is smaller. For larger area, pressure is smaller. So we've done this for solid yesterday, but if we put liquid here, we say pressure we act in all direction in the liquid. Is that okay? We've mentioned this earlier. Then let's take a look at the application in hydraulics. This is a car braking system, the ABS. Okay, this is the brake system. When you mash your brake, this is the brake part in the car. You know the brake part is connected to your tire, your wheel, the car wheel. Okay, there are pistons that hold to the wheel. Okay, on both sides, both the back and front. So on this part, we push this piston here to cause the liquid. There's a liquid here, usually oil. Okay, a fluid. This fluid, transmission oil, we call it transmission oil. This fluid will flow to both the back side and the front side. So on this back side, when it gets here, this liquid will now push this piston. There's another small piston that will now make this liquid will push it to make contact with this wheel. And once it makes contact with the wheel, it will start to stop the car, slow the car's movement down. Similarly to the front side, there are two big pistons here and here. Once the liquid flows to the tire, it will try to push the piston against this wheel to slow the disc down, the wheel disc, to slow it down, and the car will slow down. So this is the car brake system, the hydraulic car brake system. Okay? Now the only thing we just need to talk about is the instrument for measuring pressure. The instrument for measuring pressure. Pressure can be measured using two instruments. One is called the manometer. The second one is called the barometer. Okay? One is manometer, the other one is barometer. Now manometer is used for we start with the first one. Manometer is used for measuring gas pressure. Manometer is used for measuring gas pressure, while barometer is used for measuring atmospheric pressure. This one for atmosphere. Barometer is for measuring atmospheric pressure. Manometer is a U-tube. It's just like a U-tube, okay? A U-tube-shaped system that helps to measure gas pressure. This one measures the gas pressure, while barometer measures atmospheric pressure. This one is for atmosphere. So please take note. This is for atmosphere. This is for measuring atmospheric pressure. Atmospheric pressure. Pressure in the atmosphere. You know the air around us, exert pressure on the materials of the substance of the container. Anything they touch, they exert pressure on them. So the instrument for measuring that atmospheric pressure is called the barometer. Manometer for measuring gas pressure. And the pressure of the gas is equal to the atmospheric pressure plus pressure due to the liquid column. Let's say if you have a container, okay, you have a container, the pressure, you know, this is open, air from the atmosphere is acting on atmospheric air is acting on this whatever is here. Atmospheric pressure is acting on it. So, and there is also the measurement of the liquid pressure due to the liquid. So total pressure, P total, P total is equals to pressure equals to P ATM. I call atmospheric pressure ATM because ATM is atmosphere. Okay, pressure due to atmosphere plus the pressure due to the liquid itself that is pushing the material. So total pressure at the bottom of any substance for a system that is not closed is pressure due to atmosphere time plus the pressure due to the liquid. The pressure due to the liquid is called rho GH. So I can simply write rho GH. So this is the formula for our total pressure. You need to know this. Okay, we need to know this. We need to know this. Pressure, total pressure acting in a substance, in most of the substances, liquid, is the pressure due to the atmosphere plus the pressure due to the liquid, which is rho GH. So in most papers, they will tell you the atmospheric pressure. They will just give you the value. Okay, and they will ask you to calculate the total pressure. Okay, so first you calculate the pressure due to the liquid, which is rho GH, which is the one we talked about, and then you add it to the atmospheric pressure, then you get the total pressure. Is that okay? Now let's take a look at a manometer proper. We say it's an instrument for measuring gas pressure. Look at it, you pour the liquid here, here's the liquid, they are at the same level on both sides. At the same level on both sides. Now when we connect it, look at it, we connect it to gas supply. Okay, and there's atmospheric pressure exerting on this liquid here. So there's an atmospheric pressure pushing this one down. There's a small pressure pushing this one, but the pressure is not high because this place is now closed. This place is closed and it's connected to a gas supply, right? So the pressure here is low pressure. This gas pressure from the gas, okay, compared to this atmospheric pressure. The pressure from the gas is higher than the pressure here. Here is pushing, and the pressure from the gas is bigger than the pressure from this. So it will push this liquid down, okay? You push this liquid down. Now to the level here, the difference between the level, you see the level this one is, this level. The level this one is, let's take maybe a red color, something more conspicuous, or orange color. See the difference in this place, where this liquid reached, where it pushed it down. The gas will push the oil. Let's say the liquid here is mercury or oil, whatever it is. Okay, so this gas will push this mercury or this liquid further down compared to what is happening here, creating a height. Here there was no height. This was when it was not connected. This YouTube was not connected. Okay, this is how a manometer works. So it will push this one up further, creating a height. So once we know the height, now we can calculate. It is this height we just need to calculate the pressure in a liquid. Remember that. Okay, because we already know the density of the liquid. If it's oil, we know the density of oil. If it's mercury, we know the density of mercury. So the pressure, this is how manometer is used to measure the pressure in a gas. How much pressure is in this gas is determined by how much this gas pushes this liquid to create a height difference, a difference in height between this point, this part connected to the gas, and this part that is not connected. So there will be a height. Remember, pressure is rho GH, density times gravity, density of the liquid. Okay, whatever liquid we decided to use, we know the density of that liquid. So the density multiplied by gravity. Gravity is a constant value, okay, times the height. The only parameter needed to calculate this pressure is the height. The only parameter needed is the height. And that height is what this gas created for us. This gas, we push this liquid down. When you push this one down, you know, when this one is pushed down, look at it originally, it was here. When this one is pushed down, it will be flowing this way up, right? So when this one pushed down to this level, this one will push up almost to this level, creating a what? If you mark it, creating a height difference, creating a height difference here, creating a height difference. It is this height that determines the pressure. Remember, it is the height that determines the pressure in the formula. You know why? Because the density of the liquid is already given to you. You already know the density of the liquid you are using, which is this value. The gravity is a fixed value. Only the height you need to know in order to be able to calculate the gas pressure. Only the height, because this gas, we don't know the pressure it's exerting on the liquid. So to know the pressure is by how much the gas itself push the liquid. So creating a depth between the two levels. Creating a depth between the two levels on the YouTube. Creating a depth between the two levels on the YouTube. Okay? So when that depth is created, a height, which we call the height, depth. When that depth is created, which is the height, it helps us to calculate the pressure of the gas. This is how a manometer is used for measuring the pressure of the gas. Because this gas is the one that is pushing down the liquid. That is exerting a pressure on the liquid and causing the liquid to flow this other side up. The gas pressure cause the liquid to flow upward. Push the liquid down so that it flows upward on the other side. So how to know the pressure of the gas, the pressure with which the gas is exerting on the liquid, is to be able to measure the depth, the height difference between the two levels, level A and level B. The height difference between these two levels. Once you measure the height difference, you use the height, you bring it to the pressure in liquid formula. You bring it to the pressure in liquid formula. You use the height, you bring the height to the pressure in liquid formula. You say pressure in liquid is the density of this liquid multiplied by gravity is a constant value. This one you don't need to know. You don't need to be looking for it. If they will not tell you, they expect you to know this. Usually we use 10, but right now Igcse is using 9.8, so you can just use 9.8. So the density, if the liquid is water, but it's not water in this case, maybe mercury, you put the density of mercury, multiply by the gravity, multiply by the height, you just measure. This one you measure with a ruler. You measure the height. If you measure in millimeter, in centimeter, you convert to meter. And then you bring the value here, and you get the pressure exerted by this gas. You get the pressure. So this is why, or this is how a manometer is used. This is a simple manometer. This is how it's being used to measure the pressure in a gas. This is how we say manometer is used for measuring the pressure in a gas. Okay, thank you. Now let's go to barometer quickly, so that we can call it a day. A simple barometer is used for measuring atmospheric pressure. Okay, I'm not here to be I just explain what you need to know. This is how a barometer is. A barometer, you have something like a basin or a trough. Okay, you pour your liquid here. You leave here to the atmosphere. You put a U-tube, you turn it upside down. You know this tube? You invert it. This is the normal tube, okay? But you turn it upside down. Okay, so that nothing, here will be a vacuum. Notice here will be a vacuum. They always ask this question in the Igcse. They say, what is here? Here will be a vacuum. The space remaining that is not covered, okay, is a vacuum. It's called a vacuum. Okay? This is a vacuum. Now, this liquid we pour in this trough. You can call this one a trough or a basin. It's up to you, whatever you want to call it. Okay, you pour mercury in this trough. You pour mercury here. You didn't pour anything inside here. Okay, don't be mistaken. Only this basin you pour mercury. Then you brought an empty U-tube. You inserted it. You turn it upside down. You turn the U-tube upside down. And then what happens is that atmospheric pressure is pushing this mercury from here and here. You know, the air is open to the air. Here is also open to the air. Only here has been covered with a U-tube that is inserted upside down. This place, the atmospheric pressure starts to push this liquid. Here also, the atmospheric pressure starts to push this liquid. So it starts to push it all the way up. Remember, nothing was inside here before. It is when the pressure here, atmospheric pressure, start to push this liquid all the way up. Also start to push this one all the way up to create a height. This is height H. To create a height. Because instrument for measuring pressure is just to be able to create a height. And this height is 760 millimeters. Okay, the normal standard one, caused by atmospheric pressure. Normal good atmospheric pressure will cause a height of 760 millimeters. Sometimes it could be less, sometimes it could be more, depends. Okay. This value, if you divide by 10, first of all you change to centimeter, it becomes 76 centimeters. So it's on exam paper, you see 76 centimeters. It's the same thing. Okay, you could see 0.76 meter. If I want to change to meter, I divide by 1000, I get 0.76, it becomes meter. It is that 0.76 meter that we will use to calculate what? Calculate the pressure exerted by the atmosphere. Okay? You know, this is the value in meter. It is this value that is caused, the height. This height, because the atmospheric pressure, what it does is to push the mercury up this place, to push it up. By how far it goes is the value we take, the height we take to calculate our pressure. Remember pressure is just real GH. Remember pressure is what? Density. When I say real, okay, don't get confused. Okay? Density, okay, times gravity times height. So, but this value already known. The density of mercury is already known. So you take the value, multiply by gravity 9.8, multiply by the height 0.76. You get the pressure. That's it. And this is how this is used for measuring atmospheric pressure. This is a simple barometer. These things are very easy. It's not a big deal. Very easy. You bring an empty U-tube, invert it or turn it upside down, put it on a base that you pour mercury in. There, you leave it for a while. Air in the atmosphere will push this liquid from here and here that is open. You know, here, this side and this side, they are open to the atmosphere. To push this liquid up, creating a height. You measure the height. That height is just brought here to calculate the pressure by the atmosphere. To calculate the pressure exerted by the atmosphere. Is that okay? So with this, we've come to the end of pressure. Thank you for joining us. See, this one is 74 centimeter. It's not up to 76. This place is a vacuum. They ask you in the exam, what is this place called? Vacuum. Okay? This is the mercury flow upward. Here, the atmosphere acts on it and push it up. So the measurement, okay, another question they ask in the exam is, where do you start to measure the depth, the H from? You don't measure the H, they say A from the bottom of the basin, B from the bottom of the U-tube, from the bottom of the U-tube. No, you start to measure it from here. The top of the mercury on the basin, the top of the mercury, where the mercury level is on the basin. That's where you measure it from. Okay, this is very critical in multiple choice question. Okay, you measure it from here, the top of the mercury on the basin, all the way to where it flowed up to, in the U-tube. Is that okay? So that's how we measure this. So here are some questions. You can pause this video to answer these questions. Okay, you can pause this video to answer some of these questions and get better. Okay, you can stop, pause here. Answer, they're very easy. They're not big deal. Okay, so with this, we come to the end of our today's class. Thank you for joining us.